Greetings, math friends. We are continuing our discussion on the introduction to limits. We are now going to look at the definition for a derivative, which has a limit in its definition. This is a really important basic definition in calculus, and we had to understand the concept of the limit to understand this definition and be able to use it. So we are going to be naming a function f, and this is still from the real numbers to the real numbers. That's going to be our domain and range, so a real number discussion. And the derivative, that's what we're going to call this thing, is a derivative of the function f at the real number value, which is x. And we're going to denote it, this is pronounced as f prime of x. So normally we have an f of x. We're calling this f prime of x. We're adding a little apostrophe to the f here. This shows that this was derived from the function that we had originally named. So we have this formula here, which if you had previously studied the formula for the instantaneous rate of change, we had this as m equals this, and that's what we called the instantaneous rate of change. Now we're taking the m away, which was previously representing slope in like an Algebra 1 class, and we are going to put f prime of x here, and there's no change in this statement from the instantaneous rate of change. So there's no new formula to have to memorize. This is just part of the definition. We also have to say this derivative is only going to be a derivative of f if the limit exists. So previously we've already discussed how we could have a limit that does not exist. So for this definition, we're going to take f and find the derivative of f if the limit exists. If the limit doesn't exist, then we cannot find this derivative. Also of note, if f prime of x exists, or we can read this as if the derivative exists for each x in the open interval a,b, where a and b again are real numbers, then the function is said to be differentiable over this open interval. So this is an important extra idea here when you're asked questions about, is a function differentiable? Well, if we know what interval we're looking at, we can make a decision on whether that can be true or not if f is differentiable. I want to look at the function f of x equals x squared. This has a domain over the real numbers, and its range is the upper plane. The directions are to find f prime of x. Over here, notice I have x plus h inside the function. So instead of just x as our input, we have x plus h. What is h? H is just a small value that we've added on to whatever starting point that we had. And we're dividing by that same small value. The limit says that this value is going to approach 0. So it really doesn't matter where you start. You're going to approach 0 because you're taking the limit. Over here, let's take a look. If I want f of x plus h, everywhere that I have an x, I need to replace it by x plus h. So this x squared needs to be replaced by x plus h squared. So now we're going to have to do a little algebra on this. We're going to have to expand this out. All right, so we're just doing double distribution for that. So we are going to, in our example formula over here, that's a part of our definition, we're plugging that in for the first part of the numerator here, and then we're subtracting f of x, which was our given function, and then dividing by h, and then taking the limit as h approaches 0. Now that we've plugged everything in, we have this that we need to compute. We have this x squared over here being subtracted out. The very first term of this is x squared, so these terms combined go to 0, so we don't have to deal with those at this point. We can then notice that there is an h in every term, so we can reduce the fraction by h. Once these extra h's are eliminated, we are left with 2x plus h. And I already said h was going to be a small number. Didn't have to be, but it doesn't matter really how big it is, because according to the limit, it's going to approach 0. So if we take 2x and we add a really small number to it, or if we add something that's close to 0, it really doesn't affect the overall size of this a whole lot. So this is f prime of x is going to be 2x. And we would say that 2x is the derivative of x squared, because we had defined this as our function f, and this is our f prime. This function is differentiable. We really haven't demonstrated what we're doing with the interval here, but the interval that we have for this function is all the real numbers. Every x is going to be good with this, but this is our derivative. The next exercise that we are going to attempt is, given f of x is x cubed plus 4, find f prime of x if possible. The if possible clause is here because when we look at the definition, if the limit doesn't exist, we're not going to be finding the derivative. So first of all, what I like to do is I like to find the f of x plus h. So we're going to plug in here x plus h, and it's going to be cubed, and then we're going to add 4. So here, it's just algebra. We're going to have to use some distribution here to get this. I'll do it with some steps. So the first step is I have squared this value, and then this is my third one to make my cube. So I have to distribute this across this. So I've distributed the x across all of those, and now I need to distribute the h across all of these. And then at the end, we're just tacking on the plus 4. So this piece right here is essentially this piece here. You also can check this to see if there's any like terms that you can bring together. If we look here, there's no other terms with an x cubed. There's an x squared here, and this has an x squared and an h. So there's one h here. You can look at this as saying two h's here. So this term here and this term here could be combined. Leave the x squares there. So we have x cubed plus x squared. And say 2h here, 1h here. 2 plus 1 is 3. So we have 3h here. So that takes care of that. Here we have single x's as well. And also we have an h squared in here. So we again can leave the x alone. If we have one h squared here and two h squareds here, that means we have 3h squared there. So we've taken care of those terms. Then we have the h cubed here. There's no other things with an h cube. And then, of course, the plus 4 is out here on the end. So this has been simplified just by gathering like terms. Again, this is going to be this first term. So let's go ahead and apply this. We want to copy all of this. So f prime of x is going to be the limit as h approaches 0 of this thing. Minus the original thing that we started with. Now we have to be careful here. It's subtracting this whole thing, so that negative distributes across there. It's subtracting this term and this term. And all of that is going to be over h. So this is what we have to begin with. Right away, we can see again that this x cubed and this x cubed minus x cubed is 0. Also, 4 minus 4 is 0. So this term, this term, this term, and this term are all gone because they go to 0. Then we can divide out in h. There's an h here, an h here, and an h here. So this h cancels with this h, cancels with one of those and one of those. And that's going to give us that f prime of x is the limit as h approaches 0. There's the denominator is 1 now, so we can effectively ignore that. We'll have 3x squared plus 3hx plus h squared. All right, so now h is approaching 0. So if h were 0, that would be gone, and that would be gone, and that would leave us with 3x squared. And this is our final derivative of this function. So f prime of x is 3x squared. At the end of this video, you'll find exercises again that you can work on. Pause the video and then restart the video to see solutions. Cheerful Calculations.